Hello friends and welcome into yet another lecture on DEM. In this lecture, we are starting with the next combinational circuits such as encoders and decoders. But before to that, to revise in short, in previous lectures we have gone through the contents like different types of adders, different types of subtractors, and then the magnitude comparators, wherein we have seen that defining the number of inputs, number of outputs, writing the truth table, and based on the truth table for each of the output variable, obtaining the K-map simplification that
We are going
getting the output value is the basic representation way of designing the different combinational circuits. And that's why here in this series again we are starting with the next blocks of combinational circuits such as the mux, demuxes, encoders and decoders. But before starting with actual contents for this, what is the need of this multiplexer and demultiplexer that we are going to check. Generally, in all the digital communication, or rather in communication, either I will take broadband communication or digital communication. In all those cases, the basic restriction on availability of number of resources in form of channel is there, and because of that, to increase the bit rate of transmission or of the reception, the multiple number of lines we are using or channels we are using either at input side and at output side. But while transferring this parallel data, we are going to convert that in serial form at the transmitter end and at the receiver end. From the serial data, it will again got converted into the parallel form of data. And this all task we are going to do to get the transferring of this parallel data in serial form, so that to reduce the number of channel requirements for the transmission operation. This is how the mux and demuxes, that is multiplexers and demultiplexers, are playing their role to reduce the requirement of number of channels into the whole communication process. So now, after understanding the need of this multiplexer and demultiplexer, we will go for seeing in detail what this multiplexer block and this demultiplexer block is going to do for us. We are starting with multiplexer, and generally the multiplexer is also said to be the data selector block. Why it is said to be data selector block? Because it is going to do the function of transmitting the large number of information units over a smaller number of channels or lines. So just in this previous example, I have told you that there are multiple number of input lines where more number of informations parallelly are coming towards the channel, but we are having existence of a single line. So out of these multiple number of lines, which line input data has to be put on this channel, that will be the role of this multiplexer. And so here in this multiplexer we are saying that it is going to function for transmitting the large number of information units over the smaller number of channels or lines. And to do this task, it has to select the binary information from one of the many input lines and direct it to the single output line. Let's see this basic block diagrammatic representation for the multiplexer block. So here the multiplexer is always specified with some number which is 2 raised to n into 1. What it indicates is, for this multiplexer, we are having 2 raised to n number of inputs which are available, and it will give only one output correspondingly from this multiplexer block. So if I am having 2 raised to n number of input, then out of these input number of lines, which line has to be connected to the output, that will be selected with the help of the selector lines. But these selector lines also will be n in number, which n we have mentioned for getting the number of input value power for 2. So here, for every multiplexer, to select the specific input and connect it towards output, we will need the help of these selector lines. And number of selector lines will be always n in general for any multiplexer block. When the design is done by using the multiplexer, we are going to use the AND gates to represent the inputs for that multiplexer, while OR gate will be used to represent the collection of the inputs for the multiplexer. And sometimes the NOT gates will be used as a selector to connect the inputs towards the output. But this is the case if we have to design the multiplexer. So majorly in designing the multiplexer, AND, OR and NOT gates will be used. Let's see one example for designing of such multiplexer. So the problem statement asks us to design 4:1 multiplexer. So here it is clear that we are having 4 number of inputs. To mark that in generalized form of 2 raised to n, we will have 4 is equal to 2 raised to 2. So n value comes out to be 2. And that's why in the next line of a solution we have mentioned that this particular multiplexer will have 4 number of inputs, which is specified as 2 raised to 2, and the input lines will be indicated by the character representations of D0 to D3, while the n value in 2 raised to n will specify the number of select lines which are required for implementation of design of that multiplexer block. So here n is 2. So that 2 we are naming as A and B variable names. As it is 4:1 mux, so the number of specified output for this multiplexer will be 1. Now to implement this 4:1 mux, according to this selection, we have to provide first the truth table corresponding to the select line and the output to be observed. As two select lines will be existing, because of that here we have to provide the 4 number of input combinations for the select line, and those 4 number of input combinations will vary from 00 to 11, and corresponding to each input combinations of a select line, we are going to present any of the 4 input lines to be presented at the output. And that's why with the first combination of AB, that is 00, D0 will be presented as output. With second input combination of 01, D1 will be presented as output. With third combination of input of 10, D2 will be presented as output. And finally with the combination of 11, D3 will be presented as the output. And here is the block diagram representation for that 4:1 mux which we have designed, which shows that it is having the input lines from D0 to D3, it is having two select lines as S1, S0, which we have mentioned here as AB, and only one output in form of a Y is presented over. Now let's take another example in which with the usage of multiplexer we have to design now the given blocks of the mean terms which we have given in these two equations. So first we will go for this mean term representation which is to be implemented with the help of this multiplexer. Whenever such like this mean term representation will be given for implementation, always the first step is writing the truth table. Here for this function we are having three variables, so corresponding to the three input variables, 8 number of input combinations we are going to note down. Corresponding to these 8 number of input combination, as per this mean term function representation, the mean terms which are present, those only we are going to mark as a 1 in the function output of these three variables. So here we are having presence of first, second, sixth and seventh mean term. So in this truth table, the first, second, sixth and seventh mean term we have marked as a 1 value for the function output to be represented, while all other corresponding mean terms as they are absent in this function, so we are mentioning those as 0. Now we want this output to be represented in terms of these variables, because in multiplexer with respect to any of these particular input combination, one of the function output will be mentioned. So here we are taking these lines for the inputs to be defined for the multiplexer and the number of corresponding output lines to be defined for this multiplexer block. As we are having three input variable, because of that the 4:1 marks is sufficient to implement this particular function. So we are going to choose 4:1 marks for implementation of this given function. But we know if I am selecting 4:1 marks, for 4:1 marks there will be 4 possible inputs which we have to define. And for 4:1 marks, by the rule of 2 raised to n number of select lines has to be specified. So the number of select lines for 4:1 marks will be the two select lines as S0 and S1. So we have obtained now how many number of inputs should be there, how many number of select lines should be there, but now we have to define how the function output will be created and what will be the assigned input variables for those all multiplexers. And for that, let's start with observation of this particular truth table once again what we have noted over here. So in this case, with respect to the input, the output function we have to define. And these inputs, if you are observing, they are going to remain constant for one of the possibilities of change of this last variable, and that's why we have to get decision that xy will be kept constant in form of a select lines, and with respect to this z variable which is going to continuously change, with respect to that the output function is going to be defined. And that's why for the two select lines x and y which are majorly remaining constant for more number of times as compared to this z, will be assigned to the select lines, and f we are going to define in terms of z. And for that, I have to look for each of the mean term what is going to happen. So let's check the first mean term and second mean term. In this first and second mean term, what we are observing is the output f is equal to the value of z. So for these two mean terms, output f is equal to z. Now next take the next in output combinations and corresponding z values. So in second and in third mean term, we are finding that this f value is equal to z complement. So we will write f is equal to z complement. Next to that, we will go for fourth and fifth mean term, where we are finding out that either f equal to z or f equal to z dash is not going to valid commonly for both of the combinations. But here we can see that we can mention the f value equal to 0. Similarly, for the remaining two mean terms also, either f equal to z or f equal to z dash is not true for both of the input combinations. And that's why here we are going to mention f equal to 1. And we are making the combination of two mean terms corresponding outputs because we are restricted with the 4 number of input lines only. And this is how the input we have to choose either as z, z dash, 0 or 1. And that's why here for the input lines the values will be equal to z, z dash, 0 or 1. And out of these 4 values, any one of the value will be presented as a f for this block of 4:1 marks implementation. Now let's go for this another example where we are finding the function of the 4 input variables that has been specified. And so here again, to start with the designing, first we will write down the combination of input variables for 4 possible input variables. So corresponding to 4 input variables, possibly 16 different combinations we are having, which starts from 000 up to this 111. And because of that, now here we are going to specify the 16 number of possible function output representation corresponding to each of the input combination specific. Now, to represent the value of f either as 0 or 1, we have to see which mean terms are present into this given function representation. We are finding in the function representation that first, third, 4th, 11th, 12th, 13th, 14th and 15th mean terms are present. So that's why correspondingly in this particular column of f, according to this mean term number, the values have been specified as 1. And at all other mean terms, 0 has been placed. Now again we have to carry out the task of which multiplexer will be used for getting the implementation of this 4 variable function implementation to be done by using the multiplexer. So here, to get that, first we will check for how many number of inputs will be needed for this particular function to be defined. And for observing that again, what we will do is, we are going to see which variable is majorly going to vary. So again, in this case, The LSB bit of D, we are observing that frequently it is going to vary. While ABC, it is going to remain constant for two possible number of input combinations which are sequential 1. And that's why we will do the grouping where ABC first will remain constant. So accordingly we will find out 8 number of different combinations in which ABC is going to remain constant, but in that the D is going to get varied. And that's why these 8 groups have been made out. After finding this 8 number of groups, we have to select what will be the output value that we have to assign from the given select line inputs. So accordingly, we will observe for F and D variable outputs in each of the grouped column. So in first grouped column, we are finding out that F is equal to D. So for the first two variables in the same group, we will get the output value to be assigned as D variable. In the next part also what we are observing is F is equal to D. Then in the next combination we are finding that F is equal to D dash. So we will keep that F as equal to D dash. Here for this particular group of mean terms, we are not finding the relationship of F is equal to D or F is equal to D dash is true for both the input combinations, and that's why we will specify now F is equal to 0. The same case is true for this combination of the input and the output variable representation, and that's why again here F we are putting as 0. In the next stage of this grouping, we are finding again F is equal to D condition. For these two group representation, again we are not finding either F is equal to D or F is equal to D dash valid for these two grouped bit combination. So we will put F is equal to 1 in each case. Now let's check how many number of input combinations we are having. So we are having first 2, 3, 4, 5, 6, 7 and 8 number of input combination. That means to implement this particular function we will need 8 as to 1 mux, which is going to have the 8 number of input lines while only one output lines will be specified for this mux. As 8 number of input lines will be there, for the select inputs we are having 2 raised to 3, that is 3 number of select lines. So the 3 number of select lines will be specified. For the select lines, the mostly constant values will be considered. So those values we are going to give as A, B, C for the select lines. Now the remaining question is how the inputs are to be get connected from 0 to 7. And for that, each group connection that we are going to check out. So see here, for first and second mean term or for first and second input, we are having F is equal to D. So here for first and second variable, the D input has got connected. In the first and second part, we are having the D input connection to be made. In the third, that means second output, we are having that as F equal to D dash. So the second input will be taken as D dash. Then the third input and fourth input both are 0. So the 0 is connected over here for third and fourth input. Again the fifth input is taken as a D. So D is connected over here, and sixth and seventh inputs both are 1. So this is how the designing of the multiplexer for the given function is to be presented. The next block is the demultiplexer. So generally demultiplexer is going to perform exactly the reverse operation of multiplexer, where multiplexer is going to take 2 raised to n number of inputs and get it converted into one number of output. While with the help of the demultiplexer, we are going to have the input which is equal to only 1, while outputs which are presented from the demultiplexer will be 2 raised to n. Again, for representing this, which output, that is output is to be presented on which output line, to specify that, here also the select lines are important, and those select lines will be also specified in this case of demultiplexer as a value of n, where n is taken as a power value for the representation of number of output for that demultiplexer block. So let's start with this, wherein we are observing that for representing the gate selector and connecting the inputs to the outputs, we are using the NOT gates, and here the AND gates will be implemented or used to represent the number of outputs for that variable. While in this case of demultiplexer, we are having only one number of inputs. So let's take the example of implementing 1:4 demultiplexer. So friends, please make here correction, it is demultiplexer design. So we are finding that number of inputs for this block will be 1, while number of outputs will be specified by 4. But 4 is equal to 2 raised to 2. So n value for this case comes out to be 2. And this n value will indicate the number of select lines required for the implementation of this demultiplexer. So 2 number of select lines will be required for implementing the 1:4 demultiplexer. And generally, in this case, based on the two input select lines and their combinations, the outputs will be presented. So let's say that if my 0 0 combination is there for both the select line inputs, which will be represented by inverted representation of S1 and S0. So ANDing of these inverted values will be taken, and with respect to this ANDing combination, the data will be presented on the first output line. That means if my select line inputs are 0 0, then the data will be presented on 0th output line. In the same way, if my combination of the symbols is 0 1, 0 1, then for that combination of select input lines, the data will be presented on the first output line. The next input combination for select lines is 1 0. 1 will be the original form of S, which is presented over here, and 0, that means complemented input for the S0. So it will be taken over here, and along with that, to this AND gate, the data will be presented. That means when the select input line value will be 1 0, with that 1 0, the value of data is outputted on the second output line. And finally, with the combination of 1 1, the data will be presented on the third output line. This is how, in the demultiplexer, with the help of the select line combination, the output line will be selected on which the input has to be presented. The next block after the multiplexer and demultiplexer we have to cover is the decoder. So basically, the difference what we are going to lie for the decoder and demultiplexer block is to be represented in terms of number of inputs and number of outputs, as well as the variation of either select line or for enable input corresponding to the decoder blocks. In case of the demultiplexers, we were having the select lines to be specified, while in case of the decoder, we are having the presence of the enable inputs. Now, in the decoder, we are having generally the representation as n to 2 raised to n decoder. While for the demultiplexer, we have seen the representation as 1 raised to 2 raised to n. So please remember these differences. Always multiplexer or demultiplexer will be presenting a single input or single output line. While in case of encoder and decoder, on both the input and output side, the different number of variables will be present. Never it is a value of 1 for either input or output in case of encoder or decoder. And that's why we are specifying that decoder will be a combinational circuit which is having n number of inputs and maximum of 2 raised to n number of outputs. So here you can see the n number of input data lines have been presented and possible outputs will be always 2 raised to n value. But in the decoder, which output has to be decoded, to get that to be known, we should have here the input combinations has to be specified. And based on the input combination, the decoder output has to be specified. And this encoder decoder will be performing the operations which are very similar to the multiplexer and demultiplexer. Decoder is generally similar to the demultiplexer. Instead of having a single input line, as like in the demultiplexer, in the decoder we will have n number of input lines. The general representation for decoder will be as n as to 2 raised to n decoder, which we can take an example as 2 raised to 4 line decoder. That means for this decoder we will be having two number of inputs specified as AB, while from this decoder we will be having the 4 number of outputs, and those 4 number of outputs will be indicated from D0 to D3. Generally for the decoder operation, which of the output we have to get as a decoded output, for that the priorities will be assigned. Priorities means with what sequence generally the outputs has to be defined. So generally the D0 output will be having lowest priority, while D3 output will be having highest priority. Now, out of these 4 outputs, only one output will be made 1 and other outputs will be kept 0 in case of the decoder output to be presented. And that decoder output will be presented based on what is the input combination that we are having. So let's say if my input combination for the two input variables of AB is 0, 0, then we are making the D0 line as a 1 and all other lines to be 0, which indicates that here the lowest priority input has been presented. But if the input combination is 0, 1, then the output which is selected is a first data outputs, that is D1, which is marked as 1 and all other outputs will be marked as 0. Please make here correction for this third row, friends. It should be 1 0, and for this 1 0 input combination, the third output line, that has to be selected, which is made as a 1 for D2 variable, while all other three input variables are represented as 0. With final input combination of 1 1, here the fourth output line will be made 1, while all other input lines will be made as 0. Now, how to represent this as a mathematical function or as a logical diagram to be represented? So here, for every output variable where 1 is specified, corresponding to that the input combinations are to be taken. To take the input combination, either the input variable is present in uncomplemented form or in complemented form, and the complemented form of an input is represented as the variable uh, gate that is used with not gate, and that's why here we are observing the input variable in uncomplemented form and its complemented form representation by using these inverter gates. Now let's check when the D0 output is 1. For getting the D0 input to be 1, we have to have the input combination as 0 0 for AB. That means both the inputs are in complemented form. So from the line of complementing, we are going to take the combination and ANDing of it will be applied, because for the decoder implementation, generally the NOT gate and AND gate only will be used up. Here the OR gate will not be used, as like the demultiplexer implementation along with the AND gate and the inversion gate. So D0 will be specified as A bar, B bar. While to make this first line on, I want the input combination of A bar, B, and that's why for the D1 to be defined, it is given as A bar, B. Then to make the D2 1, the combination should be 1 0. It indicates it is A B bar. So A B bar will be obtained for input connection of this AND gate to give the D2 value. While to represent a D3, I should have both the input variables in uncomplemented form. This is how the output variables for the decoder has to be defined from this given truth table. Now you will ask, what is the advantage of these decoders? Because for multiplexer and demultiplexers, we have told that restriction on the number of channels in the communication process is existing, and we have to convert either parallel lines in the serial form to to match with the restricted number of channels available into the communication process. Then what this decoder is going to do? So whenever in the operating devices such as your CPUs, either one of the memory locations we have to choose from the given whole memory bus, then we have to have this decoding operation to be done to select one of the address lines from the whole memory base. That means here in memory location, selection will be done according to the binary value that is placed on address lines of the memory bus. And this address decoders will be always with n inputs, which are going to select possibly 2 raised to n number of locations out of the whole number of address locations available for that memory. So one of the decoder which is majorly used in different digital circuits is specified as BCD to 7 segment decoder. So here BCD stands for binary coded decimal, which is going to represent only 0 to 9 decimal values for binary representation, and 0 to 9 if I have to represent for binary conversion of 0 to 9 decimal numbers, I will need 4 number of bits representation for each of the decimal digit to be represented. So, one decimal value will be represented by using 4-bit group binary representation of BCD value. And generally, this BCD to 7 segment decoder will be used in the digital displays, and those digital displays will consist of the 7 segment LED, which is used to display the decimal numerals in the digital systems. For example, either in electronic calculators you can see that, and or in the digital watches also you can observe the usage of BCD to 7 segment decoder, where this 7 segment display will help us to display the numeral values from 0 to 9. By using such type of display devices, the data will get converted from some binary code to the code which is required for display. So that binary code is said to be BCD code, and code required for the display will be the 7 segment decoding. That means for any of the numeral to be displayed, which segments out of the 7 segment are to be made on and which are to be kept off. That code has to be decided. And generally here the binary code which is used for this conversion is BCD. And the restriction for BCD numbers, I have told you that they are capable of only representing 0 to 9 decimal values. And for each decimal value representation, it will need 4-bit group combination to represent it. So let's see in this 7 segment, which segments are mentioned at what place. So we are starting with this particular diagram. So in 7 segments, this upper one segment will be always represented as A. On the right hand side, the vertical 2 segments will be named as B and C respectively. Then the lower segment will be mentioned as a D, and again on left hand side 2 vertical segments will be named as E and F, and the middle segment will be mentioned as G. This is how the naming convention for all the 7 segments of the LED display will be followed everywhere in the world. Now, after that, we will see to make the digit displays of 0, 1, 2, 3, 4 up to 9, which segments out of these A, B, C, D, E, F, G are to be made on. So to display as a 0, except this G segment, all the segments should be put as 1. So in this truth table, what we are finding out is the decimal value 0, which is represented by binary equivalent by using 4-bit group value as 000, and corresponding to that 0 decimal value, to represent it, all the segments except G should be made as 1. So here you can observe from SA up to SF, all the segment values we have put as 1, and the SG we have put as 0, because the middle segment should be off to display that as 0. Now the next display value is 1, and to make that 1 to be displayed, B and C segment should be made on while all other segments should be made off. And that's why here in the BCD equivalent value of 0001 representation, the SB and SC are made 1, but all other segments have kept 0. Similarly, the decimal value of 2 will be represented by BCD value of 0010, and to make that 2 to be on, we will need A, B, G, E and this D segments to be made 1. So correspondingly check out A, B, D, E and this G segment have been made 1, while all other segments have kept 0. In the same way, for all the remaining numerals to be displayed, the corresponding on and off segments have to be checked, and accordingly to the on segment needing, we have to put the value as 1 into this truth table, and for the segments which are to be kept off, the value of 0 has to put in the corresponding segment display. So we are finding here that for the BCD to 7 segment display will be having this 4 input combinations of the bits will be taken corresponding to this 4 input combination bits. As per this truth table, the segments will be made on or off. But generally, for such like this BCD to 7 segment decoder displays, we are having either the configurations which are mentioned as common cathode or common anode for the LEDs to be displayed. If for the LED stands for light emitting diode, and you know that for the diode either we are having the two terminals, those are anode and cathode. So out of those two terminals of anode or cathode, if for all the diodes the anodes are combined and they are connected to the 5-volt supply, then that particular combination of the 7 segment display will be said to be the common anode type of displays. So let's check here. For this A segment, this is your LED. For the LED, the anode will be connected to plus V. For B segment, again this is the LED. For that again anode is connected to 5 volt. Similarly, for this C segment, the anode is connected. For this E segment, the anode is connected. For G segment, the anode is connected, and that all combination has been connected to this plus 5 volt. In the same manner, for the remaining segments also, corresponding LED anodes will be connected to plus V volt. And if such like this combination is present, it is said to be the common anode type of 7 segment display. While in this picture, if you are observing, corresponding to each LED segment, the cathodes has been combined together, and those cathode connection has been given to the ground. So this like configuration representation is said to be the common cathode type of configuration representation. So friends, here we have seen now the concept of 7 segment display, BCD to 7 segment display, how it is obtained, what are the types of two types of LED displays, that is common anode and common cathode type of displays, and how the truth table for the decoders has to be mentioned. Generally, the application of decoders is always going to lie in the counter system, because the counting value we have to display. Apart from this, it will be used in analog to digital converter, where we have to represent the digital values. The decoders can be used to drive the display systems. The next topic what we are starting is the code converters. And the code converters are nothing but the combinational circuit which changes the data presented in one type of the binary code to the another type of binary code. But now the question comes into mind, what is this binary code? So binary code is nothing but representation of text or the computer processor instructions by using the binary number system's digits of 0 and 1. So either computer instruction or the text we are going to represent in the form of zeros and ones, or the group of zeros and ones. So the binary code will assign a bit string to each of the symbol or instruction. And as it is going to code instruction or a symbol, so for every instruction or for every symbol, the separate binary code will be assigned. So for this binary code converters, we are having multiple number of code converters which are available. The first code converter is binary to gray code converter. Next is gray to binary code converter, BCD to XS3 code converter, XS3 to BCD code converter, binary to BCD converters, BCD to binary converters, gray to BCD converters, BCD to gray converters, and 8421 to BCD converter. So what these converters are, those in detail with their block diagrams, their truth table writing, and the K-map simplification we are going to see in next lecture.